Okay, let's go ahead and get started. So I apologize if you're watching this remotely. Our power is out, lost connection to Google Meet. So I'm going to try to keep this lesson short so you're not watching a very long video. But today we are covering 18.2, Developing Energy Technologies. We do not have any assignments due. So you just have a nice 3-day weekend. And we'll pick up with some electricity topics Tuesday and Wednesday of next week. So we're covering developing energy technologies today, electricity and efficiency Tuesday and Wednesday of next week. And then that puts our Chapter 18 exam on Thursday. If you could please load up your 18.2 guided notes, which you completed last night. So our goals are to describe 3 alternative energy technologies. We want to identify 2 ways that hydrogen can be used as a fuel source in the future. We want to explain the difference between energy efficiency and energy conservation. And we want to describe 2 forms of energy efficient transportation. Additionally, we should look at some ways in which we can conserve energy in our daily lives. Some key terms for us are alternative energy, ocean thermal energy conversion, or OTEC for short, fuel cell, energy efficiency, and conservation. So we've been learning about energies, non-renewable being fossil fuels and nuclear, and then renewables being wind, solar, biomass, hydroelectric. The difference between renewable energy sources and alternative energy sources is that alternative sources are energy sources that are still in development. They are renewable, but they're not really fully implemented yet. Okay, we're working towards a future where we will have them implemented. So these are renewable energy sources that are still in development. So if we were to categorize our energy, we have energy is the main category. We have our non-renewables, then we have our renewables, and then branching off of renewables, we have alternatives. So our alternatives, I'm not going to bother even trying to write these, but non-renewable, renewable, and alternatives. The 2 goals for alternative energies is that they are cost effective, so they are incentivized economically to replace the existing energy sources. Government funding is often necessary to fund the research for these, because if you think about it, while we could develop these great technologies, if they're too expensive to implement, then it's kind of pointless. There's no situation in which an economy is going to replace cheaper things with more expensive things just because it's good for the environment. Okay, it has to be economically incentivized, has to be cheaper, otherwise it's never going to be used. And not only does it have to be cost effective, the whole goal of being alternative energy is that it's environmentally friendly as well. Okay, so those are 2 things that we need to examine when we are trying to find these alternative energies: cost effective and environmentally friendly. A lot of these things, when we develop them, they might not be cost effective right out the gate, but that is something that later down the line they can become more cost effective. We talked about tidal power yesterday, so I'm not going to go over this again, but tidal power is not widely implemented, and so therefore it's categorized as an alternative energy right now. One that we did not go over yesterday was OTEC. This is ocean thermal energy conversion. So what they do, so if you think about the ocean is going to be warm at the surface where the sun is heating it, and it's going to be cold at the bottom. And so what OTEC does is it uses that temperature gradient from warm to cold, and it pumps the cold water from the bottom, and it uses the sunlight for the warmer water, and we're able to get energy from that temperature gradient. Okay, so we're using hot and cold temperature gradient to produce electricity. About 1/3 of the energy that's generated is used to pump the water. So this is not the most efficient technique of energy production. And so that is one problem that we run into. This is being experimented on in Hawaii and Japan, and the environmental impacts haven't really been studied extensively. But this is a possibility for in the future. Another consideration that needs to be made for OTEC is that in order for these to work, they have to be in deeper waters, which means once electricity is generated, you have to get that electricity to the mainland where it's going to be used. And so what are you going to do? You're going to make wires? So there has to be some method of transporting that energy. Talking about energy transport, one of the big problems with energy is the fact that we do need to transport it. Yeah, we have our wind farms, we have our solar farms in the middle of the deserts, but our problem with these is that the energy is produced at remote locations. And so we run into the issue where we need to move that energy. And the thing is, moving energy with electricity is a very expensive process. You need very long wires, and then if the wires aren't thick enough over long distances, the electricity is actually lost due to something called resistance. So to minimize resistance, they have to make the wires wider in diameter. You'll learn more about this your senior year in physics, but that's not the point. Fact is, it's very expensive to move electricity long distances because of the amount of copper that is used to produce those wires. We need thick wires to reduce the resistance, and then we need obviously very long wires. Okay. The only other way you're going to transport electricity other than through wires is through batteries. And batteries are also very expensive, and they can't hold a lot of electricity, and then they're very bad for the environment to produce. So one possibility in the future would be using hydrogen as an alternative to wiring electricity from power plants or using batteries. Hydrogen is the most abundant element in the universe. The stars are made of hydrogen. Stars fuse hydrogen into heavier elements like helium, and then later stages of the star's life into iron. So there's plenty of hydrogen in the universe. And so on the surface, this might be like, yeah, let's use hydrogen if there's so much of it. Problem is, hydrogen is relatively uncommon by itself on Earth. Hydrogen by itself is H2 molecular hydrogen. Most of the hydrogen on Earth is in a different form. It's either combined with oxygen to form water, or it's combined with carbon to form a variety of different fossil fuels, hydrocarbons. And so in order to get hydrogen here on Earth, we need to either get it from the fossil fuels or from water. Anything that has hydrogen in it, like our fossil fuels and water, we can get it. We can get the hydrogen out. It's just a matter of determining which chemical process we need to employ to get it. The problem with it, well, each one has their own problem. First, the most obvious method would be to just get it from water. Because if you take water and you undergo a process called electrolysis, if you look at the morphology of this word, lysis means to split. So we already talked about pyrolysis, pyrolytic fracking of hydrocarbons. So that means to split those into smaller components that form gasoline. So lysis means to split. Electrolysis is splitting with electricity. So if I take water and I put a current through it, I'm going to split it into oxygen and hydrogen. Hydrogen is flammable in the presence of oxygen, and that's where we can get that energy, is because hydrogen is flammable. Okay? And it also reacts violently with oxygen. So that's one way of getting hydrogen. The most common way of getting hydrogen, so this is the way that we use the most, because it's the easiest, is steam reforming. We take any fossil fuel and we add water, and that produces carbon dioxide and hydrogen gas. What's the obvious problem with steam reforming? Go ahead, Anina. You are losing energy because we have energy stored in the methane, so that's part of it. Kimmy? Good. It's emitting CO2, our greenhouse gas that we're trying to avoid in the first place. So hydrogen as an alternative energy it's still producing CO2. Steam reforming produces CO2. Okay, so that's obviously a big problem. So if we're going to be using hydrogen in the future, steam reforming can't be on the plate. Okay, we have to focus on electrolysis. And what's the problem with electrolysis? You need electricity, right? If hydrogen is supposed to substitute electricity generation, and you need electricity to get the hydrogen, that doesn't work out. So in that manner, hydrogen is actually not its own energy source. It's better thought of as a way to move energy around. We can convert electricity to hydrogen energy and then use combustion to get it back out. Or we could get the energy from a fossil fuel, come out with water to use to store it in hydrogen. So hydrogen is kind of like an energy storage mechanism, but it can't be a successful alternative fuel by itself for two main reasons. We have to use fossil fuels to get it, or we have to use electricity to get it, which, how do we generate electricity? Probably fossil fuels. So it may or may not be renewable, depending on how the hydrogen is obtained. Hydrogen fuel can be made from any material that contains a lot of hydrogen through steam reforming. Once we have the hydrogen, we can convert it to electricity using fuel cells. Fuel cells use this reaction. And you'll notice it's the exact opposite of the reaction of electrolysis. Electrolysis splits water into oxygen and hydrogen. Fuel cells take that hydrogen and the oxygen and they recombine it to produce the water once again, but we also get electricity and heat. So the hydrogen is kind of just a carrying mechanism for that energy. If I were to look at the overall process, so for electrolysis, we take water and then we split it into hydrogen and oxygen, and when we're ready to use that hydrogen, it gets recombined into water. So electricity goes in and then it comes out. Okay, so overall, hydrogen is just the intermediate. We get it to hydrogen and then we get it right back out. We put the electricity in. So we put the electricity in here and then we get it back out here. So hydrogen is best thought of as an energy carrier rather than an energy source for that reason. It can be combined with other energy technologies. For instance, maybe we could have a windmill in a remote place, and that windmill produces electricity, and we could then use that electricity to do electrolysis to produce hydrogen. And then that hydrogen can maybe be piped. Oh, wait a minute, that uses a lot of metal to produce those pipes. Maybe it could be trucked. Oh, wait a minute, if I'm going to be using a truck, I'm using fossil fuels. Somehow, that hydrogen can be transported to where the energy is needed. We always run into the problem where energy is produced in remote places and we have problems of getting it to where we need it. This is how a fuel cell works. Hydrogen in, oxygen in, water out, electricity generated. So electrons are flowing, and that is electricity. Advantages of hydrogen can be cheap. There's no emissions at the point of operation, which means when I'm operating a fuel cell, look at the emissions: water, electricity, heat. There's no carbon dioxide, there's no NOxes or SOxes, no nitrogen oxides and sulfur oxides, there's nothing like that, it's just water. So no emissions at the point of operation. 100% clean if hydrogen is obtained via electrolysis using renewable energy. It's compact, so I can compress hydrogen into gas cylinders, makes it portable. Disadvantages: it's inefficient methods of obtaining. So steam reforming, not the greatest because we're using fossil fuels. Electrolysis, not the greatest because we need to use electricity. And then there just isn't a lot of supporting infrastructure. Okay, we haven't been supporting the technology to make hydrogen vehicles, for instance. There are some companies out there that have the hope of developing that technology, but it's a long ways away. We don't have anything that is hydrogen powered, really. Okay, so even if we can start using hydrogen more, we just don't have the infrastructure for it. And then obviously storage is an issue. Compressing those gases into tanks is all fine and dandy, but where are you going to get all those tanks? And isn't it a risk if you have compressed gases that are flammable? It is. We're going to cover energy efficiency, transportation, cogeneration, this stuff next week. But just to give you a brief rundown to cover what was in your guided notes. Energy efficiency is the percentage of energy put into a system that does useful work. So we want a high percentage. The higher the percentage, the more energy efficient that is. So useful energy out divided by the useful energy in, we want that to be as close to 100% as possible. However, there's no such thing as something that's 100% efficient. There's always going to be energy loss, often from heat. The first law of thermodynamics says that all the input energy is going to be equal to the output energy plus heat. Energy is conserved. We're not making new energy. We're not getting rid of old energy. All the energy in the universe is the amount of energy you have. But there's another law of thermodynamics that says heat is always, or energy is always spreading out. The fact that energy is always spreading out, that's where our heat comes in. That's where our inefficiency comes in. Okay, most devices are fairly inefficient. Fairly is kind of an understatement. Most devices are very inefficient. Think about a car engine. If a car engine was purely efficient, it wouldn't get hot. The fact that a car engine gets very hot tells you it's very inefficient. In a perfect scenario, you put gasoline in the car, the gasoline will be converted to kinetic energy to make the car go. The fact that you can open up the hood of a car and put your hand on the engine and burn the skin off your hand is a testament to the fact that there is heat loss in the use of an internal combustion engine. That's just one example. Think about light bulbs. If light bulb's on too long, it's very hot, you can't touch it. Why? It's losing energy. Not all of the electricity is being converted to light. Some of it's being lost to heat. So these are some efficiencies of some common things. Incandescent light bulbs, 5% efficient. Fluorescent light bulbs, so CFLs, 22%. Okay, so even then, you might not be old enough to remember, all the light bulbs used to be these incandescent light bulbs where you had the filament in the inside and it would glow, and that's what created the light. Nowadays, most light bulbs are these fluorescent light bulbs, like the ones we have in the ceiling, or the more compact versions where it's like a spiral, the little tubes in a spiral, a CFL, compact fluorescent light bulb. There was a big movement to push away from incandescence to fluorescence. And the whole premise was, you're going to save all this money, and we're going to make everything more efficient in terms of the electricity. And while we did increase efficiency up to 4 times, we're still super inefficient. We went from a 5% efficiency to a 22% efficiency. Yeah, that's a big increase, but we're still super inefficient when it comes to light generation. Internal combustion engines for gasoline cars, 10 to 15%. What does that mean? That means for every gallon of gas that goes into a car, only 10 to 15% of it is actually used to power the car. The rest is lost to heat. Okay, that's very inefficient. Your human body, inefficient as well. 100% of the energy comes in as food. Only about 20 to 25% is actually used to do useful work. The rest is lost to heat. Okay, we have body heat. That is actually loss of energy. Steam turbines. So the steam turbines that are in most power plants, coal, oil, nat gas, nuclear power plants, geothermal, biomass, they all use steam turbines. A steam turbine is 45% efficient. That means I could put X amount of fuel into a power plant, and 55% of that is lost to heat, and we're only actually harvesting 45%. Solar energy is even more inefficient. Fuel cells, one of the highest efficiencies we have, are only 60% efficient. We have extreme amounts of energy loss due to heat for all of our energy conversion devices. We're trying to develop technologies to try to ramp up these numbers. One of those technologies is hybrid cars. So hybrid cars, they use a small, efficient gasoline engine. So the smaller the engine, the less heat loss. But they can switch to an electric motor when more power is needed. So they have a motor that's shut off a lot of the time. Engines can automatically shut off. So some of you, maybe your parents have cars where you're at a stoplight and the car literally shuts off. And when you take the brake pedal off, it'll restart. Raise your hand if your family has a car like that. Okay, they are becoming more popular. My car does that. If I asked this question a couple years ago, there'd be very few people, maybe one or two. Now I have 4 or 5 people raising their hand in here saying that they have cars like that. So technology is moving very quickly. Braking power is stored as electricity in a battery, and then making cars more aerodynamic as well. Think about the cars of the 60s and the 70s, maybe even the 80s, very boxy cars. Now today we have a lot of smaller vehicles that are more streamlined. So this is the premise for a hybrid vehicle. You have your gasoline engine, and then you also have the backup electric motor. You have the inverter and generator. So the inverter allows braking power to be converted to the battery storage, and then when needed, the motor can run off the battery. Hybrid because it has gasoline and electric. There's cogeneration. This produces 2 different types of energy from the same source. So wasted heat from industrial furnaces can be used to heat water to turn a turbine. One example is in Osage, I think you say Osage, I'm not positive, Iowa. There's incentives for being more energy efficient, so this drives down energy costs. So that's another method that could be used to save energy. Energy conservation, and the average household spends $1,500 on energy bills each year, so mainly for electricity, but sometimes people have natural gas as well. Most energy lost in homes is lost through poorly insulated windows, doors, walls, and roofs. If you drive around during the winter after a couple days of continuous snowing, and you look at houses, the houses with the icicles on them, those are the houses that are the most inefficient. How do I know that? Well, when it snows on the roof, right? Well, if the snow melts off the roof, where does that energy come from? Well, it comes from inside the home. So the better insulated homes will have snow on the roof and it won't melt. Why? Because the energy is kept inside the home. Homes that aren't very efficient, the energy escapes through the roof. Yeah, the internet keeps on going in and out. I'm recording the lesson and posting. That's all I can do. All right, bye. Okay. So yeah, you can know if a house is energy efficient or not based on the snow melt on the roof. If the snow is melting on the roof, that means heat's escaping the home and it's not very well insulated. So it melts off the roof and it drips off the house and it forms icicles. So if you have icicles on your home, that means you have a poorly insulated roof. You can use Energy Star products mainly appliances that are designed to be more efficient. So if you are shopping for, let's say, a new refrigerator, you can go on the website or there'll be like a sticker and it'll say the energy consumption for that product. So you could shop and pay a little bit more for one that's a little bit more efficient. And if it's more efficient, you're going to have dollar savings in electricity costs as well. So Energy Star accomplishments, this is from 1992 to 2016. 85% public awareness that the label is a symbol of energy efficiency. $362 billion saved on utility bills since 1992 for all of the Energy Star products sold. And 2.5 billion tons of greenhouse gases reduced since 1992. This is quite the accomplishment for this company, Energy Star, selling Energy Star appliances. In Copenhagen, Denmark, companies provide free bicycles in exchange for publicity. Anyone wishing to use a bike is free to borrow one after paying a refundable deposit. The program helps cut down on pollution and auto traffic. These are all parts of your home that can be enhanced for energy efficiency. Heating and cooling appliances, cooking appliances, water appliances. Those are all areas where you could buy better devices that use electricity. Unused rooms not heated. So if you don't heat that area, you're going to save a lot of energy. If you have better ventilation, you use biomass, so a fireplace in your home rather than electricity. That could be more efficient if you have a supply of wood. Shutting off the lights when you're not using them. Weatherizing your windows. Windows offer, well, no, they don't offer. They present a problem in that they're the most likely place for heat to escape your house is through the window because the glass is very thin compared to a wall with insulation. So some people, so you could buy plastic to cover your window during the winter, and it creates a pocket of air between the plastic and the glass, thus insulating your home a little bit better. Energy conservation tips: walk or ride a bicycle for short trips. So maybe you live not very far from the corner store and you need, I don't know, you want to get a snack, you want to get a coffee or something. Rather than getting in your car, starting the car, going, parking, restarting the car and leaving and coming back, you just walk or ride a bike. Not only is it healthy, but it's also saving a lot of energy and it's saving you money. You can carpool or use public transportation whenever possible. So maybe you live in a remote area and you're going to, you want to go to the, so let's say I live in Bradford. Okay, Bradford is a relatively remote area of Pennsylvania. Okay, people from Bradford, when they want to go shopping, what do? They can either do Amazon, or if they want to shop in person, they got to go to either the Galleria in Buffalo or Mill Creek Mall in Erie. They got to drive some distance. So it would be beneficial for them to decide, okay, well, we're going to go to the mall this Saturday. We should see if anyone else maybe wants to come with us. Okay, so maybe I'll call up my friend and be like, hey, we're going to the mall Saturday. I know you were talking about it a couple weeks ago. Instead of you going on one day and we going on another day, why don't we just go on the same day and share a ride? Okay, so that would save a lot of energy. You could drive a fuel-efficient automobile. You could choose Energy Star products. You could recycle and reuse products whenever possible. You could set computers to sleep mode when they're not in use. Okay, how many people have a computer at home right now and it's on while you're at school? Okay, some people do that. They just leave their computer on all day. You could save a lot of electricity by putting it in sleep mode. This is wind power in the United States. Wind power is one of the most efficient generation methods. After the windmill is made and produced, that is. You could see some of the areas with the most wind coverage are going to be this dark blue, red, and purple. So Northern California into Oregon. Off the coast of Maine, a lot of the coast of Carolinas. Okay, you can see coastal areas are the best wind generation. Areas that don't have very good, they have fair or good, but not the best, would be inland. You see a lot of coastal areas off Alaska has a good wind generation. And then wind power projects, you could see that the green squares are all the wind power projects. So there's a lot of untapped potential off the coastlines, you can see. That's it. So I'm going to end the lesson there, keep it short so that this video is not too much of a burden to watch. And that's it. We've covered our guided notes. Just a reminder, next week we're going to get a little bit more into electricity, how it works, and then energy efficiency. That is all I have for today, and that concludes this lesson.